So the next subject is Lagrange Interpolation, Chapter 3. And interpolation is going to be our big thing for the next, 3-4 weeks, heading up to exam 2, mostly dealing with interpolation in various kinds of forms, approximating functions. Now, you might say, well, we don't need to approximate functions because we've got technology, and that is true, but it's still a worthwhile thing to learn, to think about, again, being numerical analysts and think about errors and trying to estimate errors, and it produces good analysis skills. So that I hope is a good thing. And we'll learn some specialized kind of methods as well that are nice kinds of things that you can implement on spreadsheets. Now, interpolation can be interpreted in different kinds of ways. Our main focus is on interpolating functions that you are used to from calculus, like, say, e to the 2x, or the natural log function, or cosine of x, or sine of x. But you could think of interpolation in another way, which we will also talk about, where you don't have a well-known underlying function, but you're trying to estimate some quantity in real life, like bond prices. We are going to go back to bonds and talk about bond interpolation. And there's yet even a third way to talk about interpolation, and that's a more statistical thing, where we're trying to see general trends rather than trying to fit data exactly. So there's kind of 3 ways of thinking about interpolation. We will not really focus so much on the statistical things, but I will maybe bring them up sometimes. So what is Lagrange interpolation? Well, I'm not going to tell you right away here the exact formula for Lagrange interpolation. If you did the reading, you know about it anyway. It is kind of complicated looking in the reading, but when we do particular examples, it's not too bad. Instead, let's pretend we haven't done the reading and we were given the task of interpolating. Is it not pretending? Is it reality that we haven't done the reading? Let's pretend you haven't done the reading, and let's talk about interpolating from scratch. Like, how would you do it if you were given this task, say, in a calculus class? Let's use a fairly simple function to interpolate. Let's use the book's example. Their main example is 1 over x, okay? So there's really no reason to interpolate this function other than for purposes of illustration. But I think it's kind of a nice illustration, so we'll go ahead and do it. Again, it's the main example in the book, though I'll pick different data points. I don't remember offhand what data points the book uses, but let's go ahead and use simpler data points, actually, than the book. Let's say we know the values of this function at some positive integers. How about 1, 2, and, well, to make the numbers work out nicer, let's use 4. Of course, I could use 3. Oops, I'm labeling this wrong. Of course, I could go 1, 2, 3, but I'm purposely choosing 1, 2, 4 for 2 reasons. Partially because it'll make the numbers work out nicer. I won't have to worry about 1/3 being 0.3 repeating. I can deal with this at a fractional level if I like as well. Fairly simple. And also to illustrate the fact that the data values that we're going to pretend we know the function at don't have to be evenly spaced. Okay? You might say it's nice if they're evenly spaced, or it's ideal if they're evenly spaced, but they don't have to be evenly spaced. The method and the theory still works. These are called nodes. Do notice that we start the subscript at 0, not 1. So x0, I mean, you could call it the 0th node. We also could call it the first node, but either way, we'll label it x sub 0. I think I'll really usually call it the first node, but it's labeled x sub 0. The second node is labeled x sub 1, and the third node is labeled x sub 2. Now, what are the function values at those nodes? You could call those y0, y1, and y2. y0 is f of x0, is f of 1 is 1. y1 is f of x1, is f of 2 is 1/2. I'll use both fractions and decimals, 0.5. And y2 is f of x2, is f of 4, in this case, is 1/4 or 0.25. In the book's example, one of their nodes is not even an integer. I don't remember offhand what they use. It might have been something like 2.75 or something like that. You should be able to handle these kinds of situations also when the nodes are not integers. So those are some data values. What's our goal? We've got 3 points. These are not on a line because the function is not linear. There's not going to be a straight line that goes through them all. There'd be a statistical straight line that would fit the trend. That would be a regression line. But we want to go through these points exactly. We're going to need a quadratic to go through 3 non-collinear points exactly. Let's go ahead and call it P2 of x. I'm calling it P2 of x as if it's a Taylor polynomial of degree 2, but no, it's going to be a Lagrange polynomial of degree 2. But I'm not yet using the formula in the reading from section 3.1 to construct this. I'm just going to say, oh, P2 of x is some unknown quadratic. Call it ax squared plus bx plus c. And you got to find a, b, and c. Again, the contrast here between Taylor polynomials and Lagrange polynomials is with Taylor polynomials, we've got one point that we're expanding about, the x0. We're trying to match up function values and derivative values near that point and get a good approximation near that point. With Lagrange polynomials, it's still a polynomial, but the method is different. We're trying to fit these points with the different x's exactly. But you do it in the way you would imagine you do it. You don't try to match up function values and derivative values. You just try to match up function values. So 1 equals f of x0, which is also y0, should be, well, which is f of 1, should be also P2 of x0, which is 1. And if you plug in 1, you get a plus b plus c. The next y value is 1/2. 1/2 should be f of x1, which is f of 2. That should equal P2 of 2. Plug in x equals 2, you'll get 2 squared is 4, 4a plus 2b plus c. And then the last one, 1/4, is f of x2, which is f of 4, and that should be set equal to P2 of 4. 4 squared is 16, so we get 16a plus 4b plus c. The setting equal to going on here is these equalities here. Set these equal to each other. And so what you see is we've got a system of 3 unknowns, a linear system of 3 unknowns to solve for a, b, and c, solve for those unknowns. So we could do linear algebra here. Augmented matrix. Fun, fun, fun. Should we do it completely or not? I kind of feel like doing it completely. Row operations, but for sake of time, I will not. Let's have the calculator do it first of all, and then I'll show you in Mathematica as well. So in the calculator, we go into, what is it? I'm forgetting, math mode? No, matrix mode. There it is. Matrix on this kind of calculator is above the x to the -1 power, right there. The 3x4 matrix, I need to edit it. 3x4. It's an augmented matrix. The right-hand side numbers are the constants, right? 1, 1/2, and 1/4. So going across the rows, we get 1, 1, 1, 1. 4, 2, 1, 1/2, and 16, 4, 1, 1/4. I guess I did this a little bit ahead of time. I'll change the second node to look like. So, okay. Now go back to the matrix mode. The math we need to do is RREF. For reduced row echelon form, TI-84 there, it's choice B. Oops, wrong spot to do it though. I need to quit, I guess. Okay, now go back to the matrix. Go to math. RREF, reduce row echelon form. Go back to the matrix menu, use the name A. Looks like little a is 1/8. If we're writing this out. Little b is -7/8 as a fraction. And little c is 1.75 7/4. A is 1/8, 0.125, B is -7/8, -0.875. And C is 7/4, 1.75. So, in other words, P2 of x is 1/8 x squared minus 7/8 x plus 7/4. Let's see how it does. F of x is 1 over x. P2 of x is x squared over 8 minus 7x over 8 plus 7/4. Plot both of these. The interval in question is from 1 to 4, the extremes of the nodes. By the way, the nodes also actually don't even have to be in order. It's most natural to do that. That's the typical thing to do. But again, the theory works even if they were out of order. It wouldn't matter what order you do these things in. You'd still get the same equivalent system of equations. The original function, let's make red, and the approximation blue. They're matching exactly at x equals 1 right there, x equals 2 right there, and x equals 4 right there. So it's an approximation. The blue is approximating the red over the entire interval. With Taylor polynomials, the approximation gets worse the further you move away from x0. With Lagrange polynomials, it gets worse the further you move away from your interval. It gets worse and worse. So it's a good approximation between 1 and 4. Okay. If we had more data points, like if we had a fourth data point, instead of using a quadratic, we'd use a cubic. If we had a fifth data point, instead of using a cubic, we'd use a quartic. If you got n data points, or actually in general, you'd write it as x0 through xn, and you'd actually say you'd have n plus 1 data points, n plus 1 nodes. You'd use an nth degree. Right? Linear for 2 points, quadratic for 3 points, quartic or cubic for 4 points, etc. Could we do the linear algebra solving in Mathematica? Certainly. I'll remind you of how. Quickest thing to do is just to use solve. A plus B plus C equals 1. Don't forget to do your double equal signs. 4a plus 2b plus c equals 1/2. 16a plus 4b plus c equals 1/4. Put those in curly braces. Then comma, in curly braces, what you're trying to solve for, or a comma b comma c. And there we have it, written as fractions. If you type them in with decimal points, it'll give you answers as decimals. You also can do row operations with row reduce. And it's nice to put the answer in matrix form. So I can do matrix form, row reduce. And if I got a palette open, like this writing assistant, I can get a matrix in there. This button there gives me a 2 by 2. If you do control comma, it adds columns. Comma starts with a C, just like columns. Control return adds rows. So we can put our matrix in here. This is an augmented matrix, so the numbers in the last column are the right-hand side numbers of the equations, or the constant terms, I should say. There we go, 1/8, -7/8, and 7/4 again. Okay. Any questions on that? So that's a quick overview of what you would do if you did not read section 3.1. What would you do if you did read section 3.1? What should you do for your homework? You should use the method in the section. The point is to learn the method. It gives a different approach. Does it work better than the other approach? That depends on what you mean by better. It is more convenient to use the Lagrange interpolation approach for the purpose of understanding errors. There is an error theorem in section 3.1, similar to Taylor's theorem, which is why we reviewed Taylor's theorem. For thinking about errors in Lagrange interpolation, we're not going to do the error theorem today, but we'll do it Thursday. Something to look forward to on Thursday. So what would you do? Let's do the same problem here. Once again, f of x equals 1 over x, excuse me. x0 is 1, x1 is 2, x2 is 4, which leads to y0 being 1 over 1 is 1, y1 being 1/2, and y2 being 1/4. You don't write the entire polynomial down at once. Instead, you use some other polynomials that are simpler and have a certain pattern to them, and then you form a linear combination of those other polynomials. The first polynomial you write down is called L sub 0 of x. Now, when the book first introduces this, they use 2 subscripts. And if I were doing it like the book, I'd write L sub 2 comma 0 of x. And the 2 would refer to the fact that this is going to be a quadratic second degree. But that's a little overkill, I think. I'm just going to use the subscript that's going to correspond to the node of interest here. Keeps it simpler. The authors do eventually get to that point, but at first they make it a little extra confusing with 2 subscripts. This is going to be a quadratic that is equal to 1 at the first node, x0 equals 1. The nodes are really the x values, not the y values. 1 at the first node and 0 at the others. And the reason this approach is used is because there's a nice systematic way to write this down. How can we make a quadratic polynomial that is 1 when x is x0 and 0 when x is x1 or x2? We could write it like this. We could write x minus x1 times x minus x2 divided by x0 minus x1 times x0 minus x2. That is going to be 0 at the 2 nodes that are not labeled with a 0, x1 and x2, right? If you plug those in, you get 0. The bottom is not 0, right? It's the top that becomes 0. We are not dividing by 0 here. And this thing becomes 1 when you plug in the 0th node, first node, labeled x sub 0. Because if you replace x with x sub 0 here and here, you get complete cancellation to a 1 in the end. So for this example, this becomes x minus 2 times x minus 4 divided by 1 minus 2 times 1 minus 4. First, 1 minus 2 is negative 1. 1 minus 4 is negative 3. So this simplifies to positive 1/3 times x minus 2 times x minus 4. Do we want to expand this? Yeah, it's usually a good idea, I think. Expand it out, simplify it. You'll get 1/3 x squared. Outside and inside terms in this product here give minus 6x, but then times 3, 1/3 will be minus 2x. And then last times last is negative 2 times negative 4 is positive 8, times 1/3 is positive 8/3. That's not the final answer. That's L0 of x. This is a polynomial, quadratic polynomial, that equals 0 at 2 and 4 and 1 at 1. Looks like that. Is what the graph of that looks like, if I've not made a mistake. For L1 of x, you do something similar. This one we want to equal 1 at the first node, which is really the second node, x1, and 0 at the other nodes. The general formula would be x minus x0 times x minus x2 over x1 minus x0 times x1 minus x2. Whatever the subscript is, that's the subscript that's missing in the top. And it's the subscript that is the first term in each factor of the bottom. Keep in mind, this is going to be 1 when x equals x1 and 0 when x equals the other nodes, x0 and x2. So with these particular numbers, this becomes x minus 1 times x minus 4 over the bottom would be 2 minus 1 times 2 minus 4. That's a 1. This is a negative 2. This becomes negative 1/2 times x minus 1 times x minus 4. Expand that out. That'll become negative 1/2 x squared. Outside and inside terms in the foiling of this would become minus 5x times negative 1/2 is plus 5/2 x. Last times last is positive 4 times negative 1/2 is minus 2. So if I've not made a mistake, that would be L1 of x. I'm hoping I'm not making a mistake here. You should maybe try to check to make sure I didn't make a mistake in all this. If I've not made a mistake, this is the polynomial whose graph looks like this. Quadratic. It's 0 at 1 and 4, and at 2, which is x1, it's 1. It's going to go a little higher here, but the maximum will be at 2.5. One more to compute because we got 3 nodes. L2 of x is 0 at x0 and x1, and 1 at x2. X minus x0 times x minus x1 divided by x2 minus x0 times x2 minus x1. That's x minus 1 times x minus 2 divided by 4 minus 1 times 4 minus 2. That's 3, that's 2, so we get 1/6 x minus 1 times x minus 2. Expanding gives 1/6 x squared minus 1/2 x. 3, yep, okay. 1/2 x. And then plus 2/6, which is 1/3. And this should be a polynomial whose graph looks like this. It's 0 at 1 and 2. And this is not the same scale as the other ones. This is going to be sort of flatter looking. It's 1 at 4. That's going to be a 1 right there. Yeah, the coefficient of x squared is closer to 0. That's going to be a wider parabola. Now, the final answer then is a linear combination of these. P2 of x is f of x0, which you could also call y0, times L0 of x, right? Remember, L0 is 1 at x0 and 0 at the other nodes. So at 1, the 0th node, x0, this is going to have the right function value, f of x0. And it's going to be 0 at the other nodes. Plus f of x1, which is y1, times L1 of x. plus f of x2, which is y2, times L2 of x. This becomes 1 times 1/3 x squared minus 2x plus 8/3. F of x1 was 1/2. It was 1 over 2. The function was 1 over x, and this x1 was 2. So we got 1/2 there. This gets multiplied by negative 1/2 x squared plus 5/2 x minus 2. And then f of x2 was f of 4 was 1/4 times 1/6 x squared minus 1/2 x plus 1/3. Now expand and simplify. The x squared term is going to have a coefficient of 1/3 minus 1/4 plus 1/24. Fun to do with this with fractions. Negative 1/4 right there. 1/4 times 1/6 is 1/24. The x term is going to have a coefficient of minus 2 plus 5/4, 1/2 times 5/2, minus 1/8, it looks like. And then the constant term is going to be 8/3. 1/2 times negative 2 is negative 1. And then 1/4 times 1/3 is 1/12. Oh, this one get a common denominator of 24. Almost done. Let's see, we'll get 8 minus 6 plus 1 over 24. Right, which will be 3/24, which will be 1/8. So that's the right answer. And then this one, get over 8. We'll have negative 16 plus 10 minus 1 over 8. And this one, get everything over 12. 8/3 would be what? 32 over 12. So yeah, this is 2 plus 1 is 3. 3 over 24, it is 1/8. Here we get negative 16 plus 10 is negative 6. Minus 1 is negative 7. Yep, minus 7 over 8x. 32 minus 12 is 20. Plus 1 is 21. 21 and 12 are both divisible by 3. 7/4 is the constant term. Same answer as before. So that's the Lagrange method. Is it better than the other one? Well, they both still take a lot of work, especially if you don't have technology. But I guess for when n is larger, this approach probably does take less work because you don't have to bother solving a big system of linear equations by hand. Before calculators and computers, I think the Lagrange method is better for larger values of n. Like if n were 10, meaning you had 11 nodes and you want to use it as a 10th degree polynomial, instead of solving an 11 by 11 system of linear equations by hand, maybe with a bunch of fractions or even maybe even worse, a bunch of decimals, I think this approach is probably better, though I've never done either way by hand myself. Okay, so it's good. And again, it does have the benefit of also having a formula that has a remainder term that's similar in nature to Taylor's theorem. Okay.